In this video, I'm going to talk about the anatomy of a learning algorithms, which is basically discussing the building blocks of the algorithms. You may have noticed through previous videos that each learning algorithm we saw consists of three parts: a loss function, an optimization criterion based on the loss function, a cost function, for example, and an optimization routine using training data to find a solution to the optimization criterion. These are the building blocks of any learning algorithm. And you saw in the previous videos that some algorithms were designed to explicitly optimize a specific criterion, a linear logistic regression SVM, and some others, including decision trees and k-nearest neighbor, I optimize the criterion implicitly. Uh, so, by reading modern literature on machine learning and taking part in different classes, you often encounter the reference to gradient descent or a stochastic gradient descent. These are two most frequently used optimization algorithms used in cases where the optimization criterion is differentiable. And what is gradient descent? Gradient descent is an iterative optimization algorithm for finding the minimum of a function. To find the local minimum, we basically, what we do is to start at some random point, it could be somewhere here, and then takes a step proportional negative to the negative of the gradient or approximate gradient of the function at the current point. And the gradient descent can be used to find optimal parameters for linear logistic regression, SVM, also neural network, which we'll talk about later. Uh, what you need to know is that for many models such as logistic regression or SVM, the optimization criterion is convex, and convex functions have only one minimum, which is global. Optimization criteria for neural network that are not convex, but in practice, even finding a local minimum is enough. We don't need to really find a global minimum. Okay, and now let's demonstrate how this thing works through an example. Uh, We used the dataset on the spending of various companies on radio advertising each year and their annual sales in terms of units sold. We want to build a regression model that we can use to predict units sold based on how much a company spends on radio advertising. And we have 200 companies. Yep. And each company has basically, as I said, a spending in millions and the sales unit. And remember that linear regression model is like f of x equals to wx plus b, and we don't know the optimal values of w and b. And if you remember, to do that, we looked at the values such that w and b minimize the mean squared root, and then gradient descent starts with calculating the partial derivative for every parameters, our parameters being w and b. So we calculate the derivative for w and b. And how we do that is really not important. It is important, but it is probably out of the scope of this class how to calculate derivatives. You should already know that. And then gradient descent proceeds in epochs. And an epoch consists of using the training set entirely to update each parameters. Uh, so this is what we have with epochs. And then how we are using is that in the beginning, at the first epoch, we initialize uh, the values w and b to zeros, and then we calculate the partial derivatives, and then at each epoch we update w and b using partial derivative. And what the thing that is controlling the size of an update is called learning rate. And we subtract partial derivatives from the value parameters because derivatives are indicators of growth of a function. If we have a derivative this is positive, then the function grows at that point. But remember that we want to minimize the objective function. When the derivative is positive, we know that we need to move our parameter in the opposite direction. And when this is negative, we need to move our parameter to the right to decrease the value of the function. So what I want to say here, like, I mean, these are all blah blah blah. Basically, what we want to do is we want to find the best WMB to minimize the mean square root. And we, as we said in the previous picture, we start at some random place, then we start moving really, and in each point we basically calculate whether the value of with some mathematical formula, whether the value of WRB are good enough or not, and these steps are called epochs. And how big these steps are, how fast basically we are going to learn, is decided by learning rate. The smaller the learning rate, the better the model will be, but there's always a compromise between the speed and the accuracy. So too small of a learning rate, I mean, it's a never ending story. So basically we need to decide basically which one is the one that we are going uh, to use. As practitioners, there are two important things here: epochs and learning rates, the number of epochs and the value of learning rate. And there is no recipe basically what is the exact value that we're going to use. We do it for each model by trial and error. And this is what happened with the example that I said at the beginning. In epoch 0, the linear regression model was quite off the chart. The more we moved forward, it became more and more close to where it's supposed to be. And then, as you see, the loss function value is kind of decreasing when the number of epochs are growing. There are several variations for gradient descent that you could use. One is mini batch stochastic gradient descent, or a mini batch SGD, which is the version of the algorithm that speeds up the computation by approximating the gradient descent using smaller batches of the training set. SGD itself has various upgrades. AutoGrad is a version of SGD that scales learning rate for each parameter according to the history of gradients. As a result, uh, alpha learning rate is reduced for very large gradients and vice versa. Momentum is another method that helps accelerate SGD by orienting the grade descent in the relevant direction and reducing oscillations. And in neural network training, two most popular SGDs are RMSProp and ADAM that are frequently used. So, in this video, I talked a lot about the things that may sound complicated, with a lot of underlying theory and mathematical formulation. The question is that, how does a machine learning engineer work in reality? Do they go deep into all these things? The truth is that unless you are a research scientist or work for a huge corporation with a large R&D budget, you usually don't implement machine learning algorithms yourself. You don't implement gradient descent or some other solver either. You use libraries, most of which are open source. A library, as you know, is a collection of algorithms and supporting tools implemented with the stability and efficiency in mind. And one of the most used one probably is scikit-learn that we have used throughout this course so far, and we're going to use it in future as well. So what I'm saying here basically is that you're using them, you just initialize the algorithm, you do model fit, you do predicting, and these are easy. You really don't go much into the underlying theoretical foundation. It's very good that you know them, because at some point probably you want to improve an algorithm, and then this is where this helps. Or you understand, you could have an understanding of why your model is not working the way that you're expecting it to work. But this is not mandatory if you're going to work as a machine learning engineer. It's enough to know what are the algorithms out there, what do they do, what are the libraries that you could use to implement them, and how you should interpret the result. And now this final slide, I'm going to outline some practical particularities that can differentiate one learning algorithm from the other one. You already know that different learning algorithms can have different hyperparameters. Uh, Solvers such as gradient descent can also have hyperparameters, like for example learning algorithm. Some algorithms like decision tree can accept categorical features. For example, if you have a feature color that can value red, yellow, green, you can use this feature. SVM, logistic and linear regression, as well as KNN, accept numerical values for all features. So it is important. For some algorithms, you can use categorical. For some, you only need to use numerical. Another difference is on the weighting. Some algorithms like SVM allow the data analyst to provide weightings for each class, and then these weightings influence how the decision boundaries are drawn. Another difference between the algorithms is that some classification models, for example, like SVM and KNN, give a feature vector only output the class, whereas something like logistic regression or decision trees can return a score between 0 and 1 that could be interpreted as either how confident the model is about the prediction or the probability that input example belong to that certain class. Another difference between the algorithm is that some classification algorithms like decision trees, logistic regression, SVM, build the model using the whole data set at once. And if you have additional labeled example, you have to rebuild the model from the scratch, whereas some other models that you haven't seen yet here, like naive Bayes, could be trained iteratively. And another difference, which is the final one that I'm going to say here, is that some algorithms like decision tree, SVM, KNN could be used both for classification and regression, while others can only solve one type of problem. It is either classification or regression, but not both. And by this, I wrap up the lecture, the videos for this week's lecture, and I wish you good luck with your quiz. See you in next lecture next week.